objective is to identify, give properties of, and graph. But when I say identify, you're going to name it. You're just going to give it a name, and those names I will tell you. Properties is not a full characteristic list, right? I'm going to give you certain descriptions, and I will tell you what they are that you have to give me. And then graphing, we're going to do a little bit by hand, but you will always have your calculator to graph polar curves. And even on the BC exam, when you are tested on polar curves, you don't have to graph it yourself. You will either have a calculator, or if the calculator is taken away from you, they will print the graph and label it for you. Okay, because you're going to be doing calculus stuff with it. So they don't want you to get stuck on the graphing part, but you do. So I'm going to highlight, yes, how you get the graphs by hand a little bit, but we're going to focus mostly on the naming and the descriptions. All right, so rose curves. So in your notes, write rose curves. This is a rose glass, stained glass window, and the rose curves take their name from this kind of shape. So I want you to get out your calculator and put it into polar mode and enter 2 cosine 2 theta. So I want you to put that in there, but while I'm doing this, okay, since I asked you to do it without a calculator, here's the things that I'm going to think about. I know this is the distance from the sinusoidal axis. I know I have no sinusoidal axis. I know that 2 cycles are in a distance of 2 pi. I know that the period is 2 pi over 2, which is pi. And then my quarters are pi over 4. So I'm going to start at 0 and plug 0 in here, and I'm going to get 2, right? Because cosine of 0 is 1, and 2 times 1 is 1. Then I'm going to add my quarters. 1 pi over 4, 2 pi over 4, and yes, I know that's pi over 2, 3 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4. And then I want you to think for a moment, using my quarters, what kind of values I'm going to get out of this. Right, I already know 0 and 4, pi over 2. Cosine of 2 times pi over 4 is cosine of pi over 2, which is 0, times 2 is 0. This is pi over 4. 2 times pi over 4 is pi. And, right, cosine of pi is -1 times 2 is -2. And if I keep going with this, you're going to see a pattern with my quarters. Right? Did I do that right? 2, 0, -2, 0, 2, 0. Okay, now I'm going to start graphing these. Whoops, I skipped, didn't I? That's why I knew I was off. 4 pi over 4, 5, 6, 7. So 0, 2, 0, 0. I knew something was wrong, and I skipped my pi, didn't I? All right, so what happens now when I start to graph these? Right, I go out to a radius of 2, 0, right? Theta is 0. Go out to a radius of 0 and rotate pi over 4. Go out to a radius of negative 2. 1, 2, and rotate pi over 2. Right, do you see what I'm going to get here? Right, and then I'm going to go back here when I get to 8 pi over 4. So that's not very helpful in trying to graph. So when I try to think about like how am I going to graph these, I need more points because all I got out of the quarters was, what did I get? Let me think about this in y equals form. Right? What would I have? I have the sinusoidal axis here. I go up a distance of 2, down a distance of 2, right? And this is positive cosine. So it looks something like that in regular y equals form. Well, I definitely see a bunch of 2's and negative 2's, don't I? And I certainly see a bunch of 0's. But what about all these values in between? What the hee-haw is going on? Well, hopefully you have put this into your calculator and you can see that what I get is something very similar to this looking. Right? I get a rose petal. I get a rose petal. So again, you're not expected to graph without a calculator. So to get the overall shape, right, you should be able to get your calculator, but know that what you're going to get from this equation. Right? These are your critical. What I want, notice that to radiate from the pole out to the tip of each one of these rose petals, how long is that? Each one of the rose petals has a length of 2, right? We don't call the length negative 2. And notice where that came from, right? The absolute value of the dilation factor was the length of the petals. How many petals did I have? 4 petals. So when I'm asking you to give me characteristics of or descriptions of a rose polar graph, here's what I want. I want the name rose. I want the length of each petal, and I want how many petals you've got. So let me capture this a little bit in the next slide. Let me give you some notes. A rose curve has the form no phase shift, no shift off of the sinusoidal axis. So the sinusoidal axis is 0. If you're thinking about y equals form, if you're dealing with cosine or sine, as long as there is no shift off of the, no plus or minus, you've got a rose. You have n petals if the multiplier, which deals with the period, right? If that is odd, you have n petals. If the multiplier on theta, which affects the period, is even, you have twice the number of petals, and each petal has a maximum length of A. Now I should write absolute value of A here, shouldn't I? Okay. So notice for hours, we had, in the previous example, we had R was equal to 2 cosine 2 theta, right? Was our example from the previous slide, right? 2 cosine 2 theta. So we were dealing with this case. We had the right form to be a rose. Then we looked at n, and remember n has to be an integer. N was even, therefore how many petals did we have? 4 petals. And the absolute value of our dilation factor was 2, and that was the maximum length. So your book uses, I don't tend to use this word, but your book says analyze the graph, right? So what I'm asking for analyze are these 3 things. Is it a rose? If it is a rose, how many petals? And what is the length of the petals? So without graphing, can't you answer that question? Right? First, notice that I have nothing added or subtracted. So this is a rose. There's my n, so how many petals do I have? And n is odd, so I have 3 petals. And the petals each have length, what? Now, where are those 3 petals though? So you have your calculator. Go ahead and put it in your calculator and look at it. But I want you to look, while you look at it, I'm doing this. And remember, this time I have 3 cycles in a distance of 2 pi. So my quarters are 2 pi divided by 3 and then cut in 4. So my quarters are pi over 6. So I'm going to take 0, add 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, see if I can count this time, 5 pi over 6, and 6 pi over 6. And you might wonder why I'm stopping there. That's okay. So hopefully you see when I put in 0 that I do get 0. When I put in pi over 6, 3 times pi over 6 is pi over 2. Sine of pi over 2 is 1 times 3 is 3. And then maybe you're not going to be shocked to see this. And now you've looked at your calculator, so you can tell what this looks like, right? Do you see that you've got one rose petal here? And then where are your other rose petals? They're along the pi over 6. So what's going on here? I got the length, right? If I think about my top of my roads there at 3 and -3, that's the length of each one of these petals. Right, that length is 3. Checks out. I was supposed to have 3 petals, checks out. but I got 3 petals and only a distance of what? Well, that's weird. Let me go to my calculator now, and I want you to change one of your settings. So you've already, I hope, changed to polar mode. But I want you to put, I also want you to change from sequential to simultaneous. Don't hit graph yet. In here, I want you to put 3 sine theta. Don't hit graph. Sine 3 theta, excuse me. Don't hit graph. Hit enter on this, on the left side until you get the bubble. Check your window. Your window is going from 0 to 2 pi. I don't need to go all the way out to -10, right? I think maybe I'll go out to about 5. And now hit graph and watch the tracing of the petals. 1, 2, 3, and what? In a distance of 2 pi, each petal was traced twice. Right? That is a feature of having odd, right? Having a multiplier that is odd in front of your theta. I'm going to put in the other one. What's the other one that we had? The other one was 2 cosine 2 theta. Notice the 2 is even. We already know we're then going to get 4 petals, but see how the 4 petal, watch the 4 petals be traced, right? You see that? It took all of 2 pi to get me the entire graph. Kind of cool. The simultaneous mode is really going to help us also when we want to graph 2 at once, which is a little foreshadowing for tomorrow. I'm sorry, not tomorrow, the next lesson, right? For instance, look at the 2 graphs together. Oh, that was anticlimactic. I already had graphed the first one. Isn't that kind of cool? Pretty. Kind of looks like a dragonfly, doesn't it? All right. So, again, when I ask you to analyze, here's what I want. The name, how many petals it has, what is the length of each petal. Okay? And you don't need to make this chart to get that information. And when I ask you to graph it, what I'm looking for is for you to go to your calculator, verify that you've got the right descriptions, and then make sure that you have the basic shape with, right, your length going out to the appropriate places, right? And that you have the placement of the petals. This one is symmetric across what we call the y-axis if we were in the Cartesian plane. These 2 are symmetric along pi over 6 and 5 pi over 6. Okay? If you're not sure where you're symmetric, you have your table you use from your quarters. Right? And that's where your radii should be centered. The middle of the petals, I'm sorry. All right, so what if it's not a rose curve? Because hopefully you can think about the warm-up. Look at your warm-up equation. That's not a rose. You don't know what it is, but it ain't a rose. How come it's not a rose? Because there's a sinusoidal axis that is different than 0 in y equals language. The warm-up graph was called a Limassol. So the equations, now it kind of annoys me, but they didn't ask me that they change what A is, right, in these equations. Notice that the dilation factor is now called B. There is no multiplier on theta. Do you see that? No multiplier on theta. So B is the dilation factor, and A is what we would think of as the sinusoidal axis. Limassol is a French word. It's actually an old French word, which means snail, right? Old English, modern English, old French. I'm pretty sure that modern French calls a snail an escargot, but don't quote me on that. Regardless, that's why the picture of the snail is there. So there are 3 kinds of Limassol that you are responsible for, but they all have this form of the equation. And the 3 types of Limassol have to do with the values of A and B and how they compare to one another. If the absolute value, so if we're just talking distance, right? So if the magnitude of A and B are the same, we say, or the graph is actually called a cardioid, right? It's like a subcat. It's like calling a special rectangle a square, right? A special Limassol is called a cardioid. And you want to think heart. A cardioid and a cardioid, one type of cardioid looks like this. Can you kind of see the heart issue there? Now, I'm going to draw a rectangular graph. Let's pretend all the examples, the pictures I'm going to give you are cosine Limassols. So this is a cosine Limassol. So let's pretend that it is, if A and B are the same, let's pretend it's 2 plus 2 cosine theta. And let's pretend you are in y equals form and graphing that, right? Wouldn't your sinusoidal axis be at 2? And then you would go up a distance of 2 to 4 and down a distance of 2 to 0. And then you would draw the positive cosine curve. Do you see how that cosine curve hits in Cartesian land the x-axis and then bounces away from it? The cardioid on the polar plane hits the pole and bounces away from it. Hits the pole or meets the pole and then bounces off of it. That is because in y equals, this graph, y equals 2 plus 2 cosine theta, hits the x-axis and bounces. That's called a cardioid graph. And this is a cardioid cosine graph. And I want you to notice that it's cosine, so it's kind of oriented, if you will, in an x direction. And further, that radius is 4. Crazy. If, again, magnitude of A is greater than the magnitude of B, your Limassol does not meet the pole and looks like this. So again, you kind of sort of see the heart situation, but it's like the heart didn't quite make it, right? So can you see the pole right here is kind of highlighted? In rectangular form, in y equals, I would have maybe, and I'm still writing r, but again, think with your y equals brain. If the absolute value, the magnitude of A is greater than B, so for instance 3 plus 2 cosine theta maybe. Now I did say, I'm sorry, I don't want to confuse you. This graph doesn't go with this equation. I just pulled this off the internet. So this looks like maybe it's a 2 this graph would look the same, but its radius would be 4. Its length would be 4 here, right? Sorry, I didn't actually graph. I just made this equation up out of my head, and I'm just making this equation up out of my head. But notice this time the sinusoidal axis is at 3, but with an amplitude of 2, I go up to a height of 5 and down to a minimum of 1, don't I? Bottom of the road, top of the road, still a positive cosine. But notice that that cosine graph does not hit the x-axis, and our Limassol does not ever touch the pole. So I say this because even if somebody gives me a polar equation, R equals, I can tell whether it's a Limassol that is a cardioid or whether it is just a regular Limassol. Now, what's the case that I haven't taken care of? My cosine graph came down and kissed the x-axis and went back up, so my cardioid kissed the pole and left it. Or my cosine graph did not touch the x-axis, and my cardioid did not, or sorry, my Limassol did not touch the pole and therefore can't be called a cardioid. You can only be called a cardioid if you kiss the pole. So what situation have I not taken care of? Yes, crossing the x-axis. And what's that going to go with then? If the magnitude of A is less than the magnitude of B, you get an inner loop. So in that case, I would have maybe the reverse. R equals 2 plus 3 cosine theta. And I get an inside loop. That's called a Limassol with an inner loop. I call it a loopy Limassol, excuse me. A loopy Limassol. So can you predict what's going to happen here? My sinusoidal axis is back at 2, but this time my amplitude, I go up to a height of 5, but I go down to -1. So what does my cosine graph do? Right? Do you see here's the x-axis? I have a part that is under the x-axis. This little part here that's under the x-axis is represented by the little loop. Right? Kind of crazy. That's called a loopy Limassol. So I keep saying Limassol. A Limassol that is cosine points right as long as the dilation factor is positive, right? So each one of these Limassol is a cosine one because it's oriented in the XE direct, kind of XE direction, right? Can you see it's longer in the X direction? If each one of these had had a negative in front of it, this graph would flip across what we would call the y-axis in the Cartesian. This would flip across. This would flip across. What do you think the sine Limassol would look like? Points up, right? Sine kind of goes with y. Points up in a kind of a y direction. If positive, if the dilation factor is positive, and sorry, I got a text here, my bad. Sorry. So right, sine would point up if your dilation factor is positive, down if your dilation factor is negative. Also, The maximum and minimum radii of the Limassol are the combination of A and B. So for instance, now again, don't pay attention to the actual, I just captured these pictures. But this long radii for the regular Limassol, this long radii from the pole would be 5. And the short radii from the pole would be 3 minus 2, which is 1. Here again, the long radii from the pole would be 5, and the short radii inside the little loop would be 3 minus 2, or 1. And again, since we're talking about length of a radii, we're talking about the magnitude. Okay, crazy, right? So let's think about our warm-up then, right? Let's go all the way back to our warm-up. So 3 minus 2 cosine theta. What is that now? If I asked you to analyze in your homework, what would that be? Right? It's definitely not a rose because you have the sinusoidal axis, right? So this is not a rose, it's a Limassol. Now, is it a cardioid Limassol though? No, because, right, you're looking at the absolute value of A is 3, the absolute value of B is 2. So look at your notes. Or more importantly, to me, I think about this graph. Does this graph in y equals form hit the x-axis? No, it is a regular Limassol. It is not loopy because this y equals graph does not go below the x-axis, and it is not a cardioid because it doesn't kiss the x-axis, so no kissing the pole. So it is a regular Limassol. It is cosine, but negative, right? So if I was to draw this on my pole, right, graph, it would be oriented in the cosine direction, but to the left. And I would go a distance of what? Radiate how far? Right, 5. And my short radii would come in and try to kiss the pole, but I wouldn't make it. Oh, that's so terrible. Terrible. Terrible graph. Right? So this distance would be 5. From the pole here, this length is 5. And the length to the non-kissy part is 1. Now let's go to your calculator and look at that. Three minus 2 cosine theta. Right, now I'm going to change my format to go to polar coordinates. Hit graph again and trace. So look at, right, the indent. How far from the pole are you? A radius of 1. But you don't hit the pole. Now as I rotate around, it's negative cosine, so I'm oriented in the x direction, but to the left. And how far is that? Right? From the pole, rotating, right? This length is 5, radius of 5. Crazy. So here is a cool website where you can go and watch some of these graphs. Right? And you can watch them trace in y equals form and polar form. Right? Isn't that kind of cool? Notice that every time I'm hitting the x-axis here, I'm at the pole. And then when I go to an extreme, a min, or a max, I'm at the length of one of my petals. What kind of, starting from 0, what kind of graph is this? Sine or cosine? Right, this is a sine graph. Right, isn't that kind of cool? Now check this out. Look at that circle. Now, when I just made a big deal about when you go below the x-axis, you're supposed to have an inner loop. But look at the symmetry of this. Look at the part above the x-axis and the part below the x-axis. As opposed to, let's see, do they have any of the ones? Oh, they don't have, well, they have a cardioid. Here's a cardioid. Can you see this one is a negative cosine, right? And hits the x-axis, kisses it. So the pole gets kissed. This is a cardioid. Cosine, so you're oriented left. I don't know if this one has a loop. Oh yeah, here's one. So look at this. Notice that this is kind of circular, but notice the part below the x-axis isn't as big in the y equals part. And that creates your loop instead of your circle. Right? Notice, right? Here, all of this is inside the loop. And here, I'm on the outside. And again, look at the extreme, look at where I am. The other extreme, look at where I am. Kind of cool, right? Oh, I did the cardioid already. Limassol X, Limassol Y. Here's another one. They literally call this the heart curve because it's right sine, right? Sine because it's oriented with what we would call the y-axis. Notice that this sine curve, though, only touches the x-axis and goes back up, right? It's a kiss. There I am at the extreme, right? That's the length of the cardioid from the pole. Right, and here's the other radius, 0. So this must have an amplitude, right, a dilation factor of 2, and a sinusoidal axis of 2, right? Because 2 plus 2 is 4. So the length of this radius is 4, and then 2 minus 2 is 0. That's our rows that we started with. You are not responsible for the bifolium, which is kind of cool. Right, again, notice the symmetry of being above and below the x-axis there. And then check this one out. Whee! Can you see, right? Got some crazy stuff going on there. You are not responsible for those ones. All right. So, analyze the curve. And I put graphs up here, but you're going to use your calculator to graph. When I say analyze, what do I want? I want the name. So, this is, right, here is your A, and here is your B. Sine means you are oriented in the y direction, but negative, right? So again, you can think about A and B and who's bigger or smaller. To me, this is just the way I always did it without memorizing those things. To me, I think, oh, sinusoidal axis is up at 3. You're going to bounce to a 5, in between 5 and 1. You do not hit the x-axis, so this is a regular old Limassol. If you don't hit the x-axis, you're not going to kiss or loop the pole. So it is a Limassol, right? Points which way? Right? And it has radii, kind of right, capital radii would be 5, and little radius would be 1. So again, I'll let you use your calculator to be a little bit more precise with this, but I do want you to be able to say that you're going to go straight down 1, 2, 3, 4, 5, and up at a 1, and then just kind of give me that general heart kind of shape, right? I mean, that's just terrible. That's a terrible drawing. It's not symmetric. It's not too pretty, right? Maybe you should do a little bit better than me, but I really just care about the orientation and those 2 points, okay? And the fact that it is pointing and that you know it's pointing down. How about the next one? This also has a sinusoidal axis, so it is some kind of Limassol. It's a cosine one, so that is an x issue. Positive, so I'm oriented to the right. So points right. Now again, I think what kind of Limassol? I think I have a sinusoidal axis at 2, but with a dilation factor of 4, I'm going to pop up to a 6 and down to a -2. So I definitely hit the x-axis, and I don't just kiss it, I cross it. Therefore, this is a loopy Limassol. Since I'm oriented right, I'm going to go out a distance of 1, 2, 3, 4, 5, 6. And the inner radius is 2. And then again, let your calculator set the rest of it. That's terrible, 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 terrible drawing. But I care mostly about your location there. Okay. So again, just to repeat, analyze means I want the name, I want to know the orientation, and I want to be able to, you don't have to write this out, but you either write it out or I have to see, right, in your drawing, because I'll ask you to graph. If I don't ask you to graph at all, then you do have to write the radii, which I didn't do here. Right? My large radius is 6, my small radius is 2. All right, let's put both of those into our calculator just to make sure. So I have 3 minus 2 sine theta. And if I hit trace, you can see there my radius is 1. And all the way around I'm going to be at 5. The next one was 2 plus 4 cosine theta. Gonna have to make my window a little bit larger in the x direction. Loopy loop. Again, hitting trace. Notice that I'm out there at 6. And that the inside loop is a radius of 2. Yes, I know that says -2. Radius is going to be positive, right? All right, one more type of graph called a Lemniscape. So, oh no, sorry, I forgot I was going to do the spiral of Archimedes. So the spiral is where I really think of this of the snail, not the Limassol, right? So the equation, and we dealt with this last week, the equation r equals theta, or y equals any multiple of theta, is a spiral. This is not as, we don't do as much calculus with spirals as we do with the roses and the Limassol. But if you graph r equals 1/10 theta, you do have to kind of mess with your, you won't get the full spiral unless you increase, don't just go from 0 to 2 pi. Like if you're going to get your whole spiral, right, you need to, because this is unbounded. This is unbounded, so it just keeps growing and growing, right? The spiral just keeps going and going and going. So you need to make your theta on your calculator. You need your theta to go like from 0 to, I don't know, start at 0 to, I don't know, maybe 6 pi or something like that to be able to see it. And also your theta step, make your theta step kind of small, like pi over, I don't know, 100 maybe, and see if you see your spiral. Again, I'm not gonna go to the calculator. We don't do a whole lot of calculus or further math with spirals, but it's a cool graph to look at. And you do need to recognize that if you just have your radius is equal to an angle, right, or an arc, that you're going to get an unbounded spiral. The next equation is called a Lemniscape. This also is not, we don't use this as much in calculus. It is bounded, but as you notice, its equation is r squared. It kind of looks like a bow tie. And of course, you can't enter r squared into your calculator. You actually have to take the square root of both sides to be able to put this in your calculator. And then, of course, you're dealing with domains and pluses and minuses and blah, 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 blah. But the length, again, is the absolute value of a, which is why you would write a squared there. So, for example, if I gave you r squared is equal to 16 cosine 2 theta, the first clue that you have that is a Lemniscape is that r is squared. And then you also have to have a multiplier on theta, and that multiplier has to be 2. Okay, so if I want you to identify this, what I want you to say is that this is a Lemniscape. And all you have to say is with length equal to not 16. Length is equal to 4. Right, so this would look kind of like, and again, you can do this on your calculator. 1, 2, 4, 1, 2, 3, 4. It looks something like, it basically looks like a rose with only 2 petals, right? It's the rose graph with only 2 petals, but we call it a bow tie. Well, it's officially called a Lemniscape. I guess I call it a bow tie. But that's all you need to say for is a Lemniscape. Identify it and give me the length of it, right? And use your calculator to give me a graph, but you can just sketch this too. Would this be a cosine Lemniscape or a sine Lemniscape, do you think? I mean, I gave you the answer because I graphed the cosine. But what do you think then? I guess I should say, what do you think the sine Lemniscape would look like? Right, a sine Lemniscape would just be oriented the other way. Okay. And again, I kind of glossed over this back here, but when I give you a spiral, that's all I need. All you have to say if I'm asking you to analyze the equation r equals theta over 10, if I asked you to graph it, you would use your calculator graph. If I asked you to analyze it, the only thing you have to give me is that it's a spiral. Okay? But when we're dealing with roses or Limassol, you have to give me more descriptions. So just a little bit more about Lemniscapes. They are cool. And this is, Bernoulli is the one that made it, right? Discovered, I guess you could say, or made it famous. If you remember locus of points from AAF, right? What a locus of points means. We did that. We had that at the end of the year last year, right? When we described ellipses and hyperbolas or whatever as a locus of points. Well, a lemniscate is a locus of point, where the product from two fixed points, distance 2a away, is a constant a squared. Right? Kind of cool, right? This is its Cartesian or rectangular equation. You don't have to know any of that. There's just a little side note. All right, so we are done with today's lesson. And again, I know the homework seems like a lot, but I think it should go fairly quickly for you. Fairly quickly. Take care. Till the next video. Bye.